All right, this actual question was off of the 2007 free response question 2, and it was part E. So this was the very last part of the question 2 in 2007. So there's a lot of thermo that you've already done prior to this point, and there's also an additional. I think there was a part like single I and double I. So part E, use both the information in the box above and the table of average bond enthalpies below to calculate the average enthalpy of the FF bond. Now, in this question, where is the FF bond? In the box, right? So what we've got to do is we're going to have to figure out what this number right here is. Now, remember in bond enthalpies. Now, Mitchell, you told me that you had to adjust something. Tell me the way that you read it. And I'm going to be honest, it's always kind of confused me. So I want to make sure we get it right. What was the way you said? All right, so delta H of the reaction is equal to the sum of the delta H of the what? Again, you can do it this way. I think the way that I had it was subtraction, but I think you have to plug in the endothermic numbers versus or you have to change the signs. But we're just going to kind of skip all that aspect of it. So I'm going to go back to this slide. Actually, I'm not going to do it on this slide. I'm going to go to this slide. So it was N2 plus 3 F2s go to 2 NF3s. Is that correct? Okay. Now, when we're doing bond energies, remember it's broken minus formed is the way I like to think about it. So again, it's broken minus formed. Okay. So using our box, we've got an NN triple bond, we've got an NF bond, and an FF single bond. So let's go back and let's look at our reactants. What type of bond from that chart would you have to use right here? Okay, very good. N triple bond. Let me tell you how they could have done this and confused you. What if in that table they gave an NN single, an NN double, and an NN triple bond? You wouldn't know which one to pick. So you would have to know how to do the Lewis structure of this thing. So real quick, little sidebar. Remember, if we've got N, how many valence electrons does N have? 5. So I'm just going to draw it like this. I'm going to say we've got 1, 2, 3, 4, 5. So how many empty valence spots does each nitrogen have? It's got 3 empty valence spots. Well, if you match another nitrogen up to it, I'm just going to put the double one over here. What can you do with all those 3 empty spaces? Now do you see why it's a triple bond? Does or does not? Good. Okay, that's why I wanted to show it to you. Because what if it had been an oxygen diatomic? What would oxygen be? It's a 2 because we have 1, 2, 3, 4, 5, and 6. Then again, we've got 1, 2, 3, 4, 5, and 6. So what would you have to do with these? You would share there, and you would share there. So oxygen diatomic has a double bond between it. So just kind of throwing that at you to make sure you're on the same. Go ahead. Say it again. That is a good question. I don't know if the diatomics count as standard states. I think if it were just the letter O or just the letter N, it wouldn't be. And the reason I say that is because according to this, the bond energy, it does have a bond energy. I guess bond energies have to have a value because you have to have energy to make and break bonds. So it'll always have a bond energy. Does that make sense? Okay. There will always be a bond energy. The delta H of formation will be 0. And again, those are still the little things that I'm mentally trying to process myself. All right. So We've got F2. What type of bond would that be, according to your chart? You've got NN triple, NF, and then FF. What's it going to be? We're just going to have FF. But here's the deal. How many of those are we going to have? 3 of them. Very good. And I'm telling you now, that's going to come into play very much so in the next few minutes. Okay? Now, what about the NF3? Okay? And this right here is where students miss this. People put 2 NF3 or NF bonds. Why? Where do you think that you got the 2 from? The coefficient. But here's the problem. How many are there supposed to be? 6. Very, very good. Why are there 6 of them? So when you look at the Lewis structure of this thing, do you agree that there are more than 1 NF bonds in this entire structure? How many of them are there? 1, 2, and 3. So in 1 NF3, you've got 3 NF bonds. But according to the coefficient, how many NF3s do you have? You've got 2 NF3s, so you have a total of 6. And so that's where everyone messed up on this particular problem, is they either put a 2 or they put a 3. That was the most missed part of this question, was that 6. People did not put a 6 there. Real quick, I want to go back to this because some of you have told me that this is probably one of your weaker aspects of this class. How many of you know without a shadow of a doubt the name of the shape of that molecule? All right, so we need to talk about that. Again, these are the things as we're going through this class that I hope that you all remember. But again, I recognize that some of you did not have me when I did this, and so the way that I taught it was probably a little more effective than you had. So the way that I always taught this was in the ABE model. Okay, now, so we've got A, we've got B, and we've got E. Now, what did A stand for? The central atom. How many central atoms are on this thing? 1, and who is it? Nitrogen, okay? B stands for bonded atoms. Okay? And then E was electron pairs, and here's the key part to this. On the central. Because in the entire molecule, the entire thing, how many electron pairs do you have? 2, 4, 6, 8, 10, 12, 14, 16, 18. That makes no sense at all. So we're totally focusing on the electron pairs on the central. So if you wrote the ABE model for this thing, there's always only going to be one A. How many atoms are bonded to the central one? 3. So it's B3. And are there any electron pairs on the central atom? Yes. So it's AB3E. And again, the way we did this, and I taught this, if you knew the model, you should definitely then know the shape. Now, how can I take this thing that I have right here? How can I make this look like that drawing? Take away one of them out, right? So if I take this out. Now, what is on the board that I can't represent on this? The electron pairs. But here's what's happening. What are these electron pairs that are sitting up here doing to these 3 Fs? They're pushing them, right? They're pushing them away from them. They don't want to be anywhere near each other. Because what do all these Fs have flying around them? Electrons. Well, what do 2 pairs of electrons do to each other? Why do they repel? They're opposite charges. So electrons and atoms want to be same repels. So because they're the same charge, they're trying to push each other as far apart as possible. So when you have this AB3 model, the name of the shape of this thing is trigonal. Now, I call it pyramidal. If you had Miss Hicks, she called it pyramidal. I don't know, Mr. Park called it. And if you read some books or hear some other people that teach this, they call it pyramidal. I personally like pyramidal. But that is the name of that shape. What about the bond angle of this thing? Very good, Claire. 107 degrees. The hybridization. Remember how I taught you to do hybridization? Draw what around each thing? Draw flower petals, okay? So again, I've already drawn, I'm going to start with the green. So I've already got a flower petal there. And again, it's around everything on the central. So that's 1, 2, and then 3. Everybody with me on this? Is this clicking? Hopefully. Maybe. It's just like a foreign language. Now, the way we do hybridization again is I'm just going to redraw it real quick. The way, again, so you can start it like this. So S, we've got 1 orbital. We can change it back to a pen so it's smaller. P, we've got 1, 2, 3. D, we had how many? 5. 1, 2, 3, 4, 5. So when we did this, we did S, P. So we have 1 S and then 1, 2, 3. So when you do your hybridization, it's S, P, 3. Okay, does that make sense? All right, now going back to this, so you told me it was sp3. Is this thing polar or is this thing non-polar? It is polar. So if it's polar, it also has an intermolecular force attached to it. What are the 3 intermolecular forces? Okay, all right. So we've got DD, LDF, and HB. Okay, DD is dipole-dipole, LDF is London dispersion force, and a hydrogen bond is HB is hydrogen bond. Now, which one of these can it automatically not be? Why can it automatically not be hydrogen? There is no hydrogen. Now, in fact, there is some bond going on because there's N and F. But it can't be hydrogen bonding because it is not a hydrogen present. Now, these two are very easy to distinguish between. Because if it's an LDF, if it's a London dispersion force, that was only between what 2 types of molecules? Non-polar. Now, you just told me that NF3 was what? Polar. So dipole-dipole is always going to be between 2 polar molecules. So automatically, without even thinking, if you know those 2 facts, then you know this has to be what type of IMF? A dipole-dipole. Okay? That's a quick down and dirty thing of Lewis structures and molecular geometry. Okay? So now, getting back to the original question, we've got all this stuff to go through. So here's the deal. Do we have a number for NN triple bond? Going back to that chart. Yes, 946. Now, the one thing I want to ask you about this that I think is interesting, 946. Compare NN triple to NF. What about the numbers? What do you notice the numbers? NF is much, excuse me, the NN triple bond is way, way bigger. There's 2 reasons why. What are the 2 reasons why it's much higher? Okay, the triple bond is the first reason. When you have more, if this were karate class, what would you need more energy to break through? 3 boards or 1 board? 3. Well, that's automatically the case. But then there's one other reason. Because in fact, NF has if it were an NN single bond, it would actually be less than NF. Because what do we know about fluorine? It's the most electronegative, right? Which means it's going to pull that nitrogen a little bit closer, which means it's a lot stronger of a bond. But because it's the triple bond, but there's something special about triple bonds in comparison to single bonds, other than strength. They're closer together. Remember, the more bonds you add, what happens to the distance between atoms? The closer they get. So that's another reason, is because they're a little bit closer, which means it's harder to break them. And obviously, you've got that triple bond. Okay? Now, NF. Well, first of all, let's go right here. Do we have a value for FF? Nope. That's what we're solving for, right? Okay? Now, again, these are going to be on the same side, so we're going to put these in brackets. And then finally, now you told me over here that this is going to be a plus. And then we said 6. And what was the NF bond value? 272. Now, go ahead. All right, that was what we were just talking about a few minutes ago. Do you agree that this NF, this one NF, has 3 NF bonds in it? But if you go back and look at the coefficient, how many NFs do you have in this reaction? You've got 2, so that's why there's 6 total. And that's why I said that that's the most missed part of this entire problem, is people either put 2 because of the coefficient, or they put 3 because of the molecule. Does that help? Okay? All right. Now, the problem is, the last part of this is I need to set this equal to something. What do I set it equal to, and how do you know? Look at this right here that I just circled in red. Do you have that anywhere in the problem? Where? Very good. Look up right here. Okay. So we're going to set everything equal to that number. So negative 246. So we've got negative 246. Now what do? Solve for x. That's all you got to do. Now, because of time, I'm just going to go ahead and show you the answer. And this is what they did. So now they've got bonds broken minus bonds formed. Why do we have plus bonds formed? That's C. So does it need? But see, let's go back and let's look at what they did. They don't have a negative. There's not a negative there, so it has to stay. But they didn't flip it either. Okay. So you basically write it down, but it needs to say subtraction. So the consensus we're coming to is that write it directly off the table, and it still needs to be subtraction. Okay, so that's the consensus. And again, I told you this was always the hardest part for me as well, is because it just kind of gets confusing in a way. So this is still minus. So let's go back in, and let's keep it subtraction. So when you do that correctly, you would have come up with 141 kilojoules per mole. I'm not grading for accuracy. All right, so let's look at the key points. Hold on a second. What did they do? What are we doing right here? Oh, they just rearranged it algebra-wise. That makes sense. I don't know why you would do that either. Yeah, I don't know why. Yeah, you guys know this. So notice what you have. You've got 1 point is earned for the correct number of bonds in all 3 compounds multiplied by the average bond energy. So you got 1 point for 1 nitrogen triple bond. You got and 3 FFs and 6 NFs. So you got 1 point just for getting the numbers right. And then you got 1 point earned for the correct answer. So 1 point, total of 1 point is earned if an incorrect number of bonds is substituted in an incorrect equation. The answer is reasonable. Now, what basically this means is you can earn a BOA. Let's say that you put 2 or 3 right here. Could you still have earned a single point, not both points? Yes, so this would have been the BOA aspect. If you messed up the 1, the 3, or the 6, you still could have earned the answer if your math worked out to be the right answer. Okay? Does that make sense? All right, the one last thing, I've already given y'all that, so I actually want to go back to this problem and do one additional thing. So if you're on the iPad, you may want to add a page. If you're not, hopefully there's some room on the back of the paper. The next question that I want to look at involves this, and this is what we're going to get to in the next few days. Because and I'm just going to write it right here. What if part F was, and this is all ahead of the game, but that's okay because we're going to get to it. Calculate delta G naught of the reaction. Up to this point, there's been only 2 ways that you guys have known how to calculate delta G. Would you agree with that? What are the two ways, as of today, that you know how to calculate delta G? Okay, one of them is delta G equals negative Nphe. Okay, and what? Very good, delta G equals negative rat length. Up to today, these are the only two ways that you know how to calculate delta G. Today we're going to add a third one, and this is the new one. And here's the acronym. So we've got Nphe, RatLink, and Ghetto Homies Take Speed. And we hadn't talked about entropy yet, but we're going to go ahead and I'm introducing the delta G aspect of it. Well, you're more than likely, every time I've seen a thermo question, you're going to have to go from two of them to the missing one. Does that make sense? All right. Now, this formula is super easy, but guess what they do just to make you mad? They don't blindfold you, no. You can use your calculator on this. So again, Ghetto Homies Take Speed. So delta G equals delta H minus T delta S. So here's what I want you to do. Everyone look in that red box up there at the top and tell me if you can see where they are going to infuriate you. Huh? Say it again. Say it louder. No. No. That's it right there. Look at your energy unit. But here's the problem. You see, I've got H, I've got S, and it says calculate G. You know how to plug those in, but you've got to catch that their units are different. And that's the number one missed problem. Again, a lot of thermo is straightforward, but there's little tricks that if you miss the trick, you script the whole thing. Because like I said, all you're doing is going to take these numbers and you're going to plug them into Ghetto Homies Take Speed. But the problem is this little part right here screws everyone up. Now, personally, I always convert kilojoules to joules. That's just how I always do it. I like to make smaller numbers bigger. That way I know which way I'm going. So when we now look at this, I'm going to change screens and we're going to go to it one more time. So we've got delta G equals delta H minus T delta S. All right. So the delta H value that they gave you was negative 264 kilojoules per mole. So we need to get that in joules, which would be what? What is that in joules? Negative 264,000 joules per mole. But again, people forget to convert this. This is where writing units really plays a big part in this, because if you wrote kilojoules and then over here you wrote joules, should your mind catch that? Hopefully, it should, but some people don't. Now, minus. Now, Logan, I think I heard you say this. Anywhere in the problem and in the question do they tell you what temperature this reaction occurred at? Very good. Now, obviously, remember, this is question E and F. We're talking about there's a lot of information before it. But right here, even if they did not state it, those two numbers tell you the temperature at which the reaction was at. So it's going to be 298. And help me out because I can't see the other number. What is the delta S? Negative 278. Is it joules per mole? Joules per mole. Okay. All right. Now, here's my first question to you. What is the sign of the delta H in this reaction? Negative. So is this exo or endo? This is exo. Are exothermic reactions TF or not TF? TF. Yeah, the 298 is the temperature. Yeah, my bad, Devin. Thank you for saying that out loud. I'm being dumb and I left that off. Okay. Now, my second question is, what is the sign of the delta S? Negative. This is where everyone always forgets this. Is is negative delta S more order or more disorder? No, we're talking about negative delta S. This is more order. Is nature okay with that? No. Nature loves what? It loves chaos. It loves disorder. So this is not TF. And so here's the reason I'm asking this question. Nature's got two fundamental processes going against each other. One process nature is preferring because it's exothermic. The other process is not going in its favor. So here's the deal. We've got to figure out what the true spontaneity of this reaction is. Because remember, you should know this by this point. There are three things that tell you if a reaction is truly thermodynamically favorable or not. What are those three things? Geek, G-E-N-K. So, H can tell you if it kind of can be. And S can tell you if it kind of can be. But the only way you truly know is if you calculate what part? G. You've got to know G. So here's what I am going to need your help on this because I do not have this in a slide. So I do need someone to actually calculate this number for me. Be very careful with your signs here. You got it? That's the answer? Okay, go ahead. Yes, it's 298 times negative 278, but then you've got to subtract that from negative 264,000. What you got? $18,11,5,6. So negative 181,156. Is that what you got? Now here's the deal. What unit would that be in? Stay with me. Stay with me. Cancel. Cancel. Now, you still have joules over mole because it's subtraction. It's not multiplication or division. But remember, we're dealing with joules per mole of reaction because it's delta G. But here's the final thing. Two questions. Number one, is that the correct number of significant figures? No. Second thing is that the best format to write it in? No, here's what I would do. I would convert this to negative 181 kilojoules per mole of reaction. And that would be your final answer. So what if part F double I was, is this reaction thermodynamically favorable or not? And how do you know? Yes, simply because delta G is negative. That's all you have to write. That's it. No, go ahead and say it. And that's, yes, this is true, but that is not true. Now, Nick, hypothetically, what if I gave you a totally different set of circumstances, that it was still exo, but this was a positive delta S? What if they're both thermodynamically favorable? Then delta G is automatically going to be negative. And here's how you know that. Math. I want you guys to think about this and with no numbers, just signs. What do we want for true TF? So we want a negative minus positive and a positive. That's ideal. Well, what is a negative minus two positive numbers? And remember, what is delta H always going to be in? It's always going to be in kilojoules. So it's always going to be bigger than the joule S. There's no way it'll ever be that way. No, because delta H's are always in kilojoules and S's are always in joules. And so delta H's will always be in the thousandths place bigger. Yes, delta H will always be bigger than delta S. Okay. What if it's true not TF? That would mean you would have a positive here minus a positive and a negative. Again, that would give you a positive number. And delta G does not want to be positive. So we good with all that? Okay. All right, we'll stop there for today because we're going to get into phase changes next or on Monday.